Hi, lovely people. My name is TTJ Kepsi Richard, and welcome to my online tutorials. Today, our discussion on ordinary differential equations will be on finding solutions to higher order non-homogeneous ordinary differential equations. Remember, we said when we are finding solutions to non-homogeneous higher order ordinary differential equations, three methods come into mind. That is the method of undetermined coefficient, variation of parameters, and the differential operator method, which is also known as the D operator method. Please do well to check out my videos on the method of undetermined coefficient and the D operator method. Today, our discussion will be on variation of parameters. So before the video ends, I will tell you how to solve non-homogeneous higher order ordinary differential equations using the method of variation of parameters. Then we'll take some sample questions and deal with it. So this will be a very interesting engagement. Be my guest. So we say non-homogeneous ordinary differential equations are differential equations that take this form. That's our R of S is never equal to 0. And we said that when we are asked to solve or find solutions to non-homogeneous ordinary differential equations, we find the solution, the general solution will be equal to the complementary solution to the homogeneous side plus the solution to the non-homogeneous side. And remember, the homogeneous side is setting up this equation to 0 and finding that. Then the solution to the non-homogeneous side is y of p. That y of p using the variation of parameters is equal to negative y1, the integral of y2, if this is g of x, the integral of y to g of x all over the raw square of y1 comma y2 dx plus y2 the integral of y1 g of x all over the raw square of y1 y2 dx. Please check out my videos on how to find the raw square of a function on YouTube. So having known this is the raw square, the g of x is the part, that's the homogeneous side equal to that function. That function becomes the g of x. Now what is our y1 and our y2? Our y1 and the y2 is gotten from the function of the complementary solution without the constant of integrations or the constant from our solution. So now we take some sample questions and see how we can find general solutions to non-homogeneous ordinary differential equations using the method of variation of parameters. So our first example says that we should find a general solution to the differential equation y prime prime minus 3y prime plus 2y equal to e exponent x plus e exponent 2s using the method of variation of parameters. Even when we are not asked to use the method of variation of parameters, if you try to use the method of undetermined coefficient here, you may fall short. So that's one importance of the method of the variation of parameters. So since we know that our differential equation is non-homogeneous, that's y prime prime minus 3y prime plus 2y is not equal to 0. It is equal to the function e exponent x plus e exponent 2s. It means that it is non-homogeneous. So our solution, our general solution, will be equal to the solution to the homogeneous side plus the solution to the non-homogeneous side. That's the principle of superposition. So the solution to the homogeneous side, we have to find that. That's we set up this differential equation to 0 to make it homogeneous. Now we let y to be equal to e exponent r of x. Then our y prime will be the differential of this. That will be r e exponent r of x. And our y prime prime will be equal to r squared e exponent r of x. After that, we substitute that into the differential equation. So in place of y prime prime, we substitute r squared e exponent r of x minus 3y prime, which is r e exponent r of x, plus 2 and our y is e exponent r of x, and that will be equal to 0. Please check out my videos on how to find solutions to homogeneous higher order ordinary differential equations. So now e exponent r of x is common to them, we bring it out. So we have r squared minus 3r plus 2 e exponent r of x is equal to 0. On divide both sides by e exponent r of x, we have r squared minus 3r plus 2 being equal to 0. This becomes a quadratic equation we solve. When you solve these quadratic equations, you get r to be equal to 1 or 2. So we can say that our complementary solution to the homogeneous side, remember these are two distinct roots, will be a e exponent x plus b e exponent 2x. So I will find the general solution to the homogeneous side. We need to find the solution to the non-homogeneous side. And so with the method of variation of parameters, our y p will be equal to negative y1, the integral of y2 g of x over the Roskian of y1 comma y2 dx, then plus y2 the integral of y1 g of x the Roskian of y1 comma y2 d of x. Now what is our y1? Our y1 is equal to the function here, that's e exponent x. Our y2 will be equal to e exponent 2x, and our g of x in this case will be equal to the non-homogeneous side, that's e exponent x plus e exponent 2x. So that will be e exponent x plus e exponent 2x. What is the next thing we need to do? We need to find the Roskian. So remember the Roskian of y1 comma y2 will be equal to the determinant of the y1, which is e exponent s, e exponent 2s, and they are differentials. On differentiate this, we get e exponent x. On differentiate it, we get 2e exponent 2x. They are. Please do well to check out my videos on how to find the Roskian of a function on YouTube. So when we do this, remember this multiplied, we get 2e exponent 2x minus this multiplied, this we get, this times this will be 2e exponent 3x using indices. Then this times this will be e exponent 3x. When we subtract, we get e exponent 3x. So that becomes the Roskian of y1 and y2. So having know everything, we substitute into this function. So our yp will be equal to negative y1, and y1 is e exponent x. So we have negative e exponent x, the integral of y2, which is e exponent 2x, of g of x, and g of x is e exponent x plus e exponent 2x all over the Roskian, which is e exponent 3x, then plus our y2. And what is our y2? Our y2 is e exponent 2x, the integral of y1, which is e exponent x, times the function g of x, e exponent x plus e exponent 2x. Remember we have the x here, all over the Roskian, which is e exponent 3x, then dx. So when we solve further, we get y of p to be equal to negative e exponent x. When this divide that, we get e exponent negative x bracket e exponent x plus e exponent 2x dx plus e exponent 2x the integral. When this divide this, we get e exponent negative 2x then times e exponent x plus e exponent 2x dx. I hope you get that. So this will be equal to negative e exponent x, the integral. Now we expand. E exponent negative x times e exponent x. Remember it will be e exponent negative x plus x. And that will be e exponent 0. Then plus e exponent negative x plus e exponent 2x will be e exponent x. That's negative x plus 2x will be x. Dx then plus e exponent 2x, the integral of e exponent negative 2x times e exponent x will be e exponent negative x. That's negative 2x plus x will be negative x. Then plus e exponent negative 2x times e exponent negative 2x will be e exponent 0 dx. So what do we have? We have e exponent minus e exponent x, the integral of 1 plus e exponent x dx plus e exponent 2x, the integral of e exponent negative x plus 1. Remember, e exponent 0 is 1 ds. So this will be equal to negative e exponent x. Now we integrate this. When we integrate 1, we get x. When we integrate e exponent x, remember the integration of exponential functions. We just differentiate the function and use it to divide. So when we differentiate x is 1. When we use it to divide, we still get that. So then plus e exponent 2x times, so the integral of this will be minus e exponent negative x, then plus our x, then plus the constant of integration. So now we multiply this by this, we'll get minus s e exponent x minus e exponent 2x. That's e exponent x times e exponent x will be e exponent 2x. Then this times this will be minus e exponent x. Then this times this will be plus x e exponent 2x. Then plus our constant of integration. Now we group like terms, we bring the e exponent 2x together and the e exponent x's together. So I have x e exponent 2x minus e exponent 2x this, then minus x e exponent x, then minus e exponent x, then plus my constant. What is common here? E exponent 2x is common. I bring it out, I have x minus 1. Then what is common here? Minus e exponent x is common. When I bring it out, I have x plus my 1, then plus my constant of integration. Then we can say this is our y of p. So remember we said that our solution to this, our non-homogeneous higher order ordinary differential equation will be y of c plus y of p. And we said that the y of c is the solution, the general solution to the homogeneous side. And when we solve, we had this. And we said the y of p is the solution to the non-homogeneous side. And when we use the variation of parameters, we have this. Then we can say our y of x, which is the general solution to this differential equation, will be a e exponent x plus b e exponent 2x, then plus e exponent 2x times x minus 1 minus e exponent x times x plus 1, then plus our constant again. So when we are given some general solution, some boundary conditions, we just substitute to get our particular solution. We'll solve one more example on this so that you'll be abreast with the concept. So before we solve our second example, please remember to subscribe to my YouTube channel if you are yet to. It is the only way you can help promote my YouTube channel so that I can record more mathematical content for you. Now pause the video and try solving this. After that, you compare your answers with mine. So the question says, solve the differential equation y prime prime plus y is equal to z. So remember, we said that when we are faced with a non-homogeneous higher order ordinary differential equation, thus the g of t is not equal to 0. In this case, it's set t. So the general solution to this differential equation will be equal to the solution to the complementary side. That's the solution to the non-homogeneous side, then plus the homogeneous side, then plus the solution to the non-homogeneous side. And we said that the complementary solution is solved by setting this equation to 0. So we say y prime prime plus y should be equal to 0. What do? We let our y should be equal to e exponent r of t. Then our y prime will equal to r e exponent r of t. And our y prime will equal to r squared e exponent r of t. That's differentiating this function, we get this. When we differentiate this, we'll get that. So what do we do next? So we substitute. So our y prime is equal to r squared e exponent r of t plus our y, which is e exponent r of t, it will be equal to 0. What is common to them? E exponent r of t is common to 0. So r squared plus 1 and e exponent r of t is equal to 0. Please do well to check out my videos on how to solve homogeneous higher order ordinary differential equation. So when we divide both sides by e exponent r of t, we can say r squared plus 1 is equal to 0. R squared will be equal to negative 1. And our r will be equal to the square root of negative 1. And remember, the square root of every number is plus or minus. Then our r can be equal to plus or minus I. And we said that when we are solving a homogeneous higher order ordinary differential equation, the root to the quadratic equation is complex, involve complex root. Then the general solution, our y of c, will be equal to e exponent r of t bracket a cos beta t plus b sine beta t, where the t here is the real part of the complex root. And remember, the real part here is 0. Then the whole of that will be 1. And the beta is the coefficient of the imaginary part. And the coefficient here is 1. Then we can say our y of c is just equal to a cos t plus b sine t. I hope you get that. So having known the complementary solution to the homogeneous part, we need to find the solution to the non-homogeneous part. And we say that non-homogeneous part will be equal to negative y1, the integral of y2 g of t over the Roskian of y1, y2 dt plus y2 the Roskian of y2, the integral of y1 g of t over the Roskian of y1 y2 g of t dt. Now what is our y1? Our y1 becomes the first function here, which is cos t. Then our y2 is equal to sine t. And our g of t is the function that makes it non-homogeneous. That's sec t. So we say to be equal to sec t. And remember, sec t is the inverse of cos, and it's the same as 1 over cos t. So we need to find the Roskian. So we say the Roskian of y1, y2 will be equal to the determinant of the y1, which is cos t, and the y2, which is sine t, and they are differentials. So when we differentiate cos t, we get negative sine t, and when we differentiate sine t, we get cos t. Now, this times this will be cos squared t, then minus this times this, so that will be plus sine squared t. And cos squared t plus sine squared t is nothing but 1. So we can say the Roskian of y1, y2 is equal to 1. Having known the Roskian to be 1, we just substitute the necessary thing and we find y of p. So our y of p, remember, is negative y1, and our y1 is cos t. So we say our y of p will be negative cos t, the integral of y2, which is sine t, times g of t, and the g of t is 1 over cos t, so 1 over cos t over the Roskian, which is 1, then dt, then plus our y2, which is sine t, the integral of y1, which is cos t, times g of t, which is 1 over cos t, then all over the Roskian dt. So what are we having? We have our y of t to be equal to negative cos t bracket. So we want to divide this by that. 1 divided by any number is a number. Then this times this will be sin t over cos t dt plus sin t integral of 1 divided by that will still be that. Cos t times 1 over cos t will be 1. I hope you get that. So we have 1 dt. So what do we have? So we know that when we integrate this, it's just t, but what of this? We need to see if one differential cos t, we get sin t. Then we can use integration by substitution. So we said we let u to be equal to cos t. Then our du over dt will be equal to negative sin t. Then we can say that du is equal to negative sin t dt. When we divide both sides by negative 1, then negative du is equal to sin t dt. So, remember this function can be written as 1 over cos t sin t dt. Then we have 1 over cos t, which is u, so 1 over u, and in place of dt, in place of sin t dt, we substitute negative du. Then we can say our y of p is equal to negative cos t, the integral of 1 over u, then sin t dt will become negative du, then plus our sin t times the integral of 1 dt. So what do we have? When this, we can put the negative out to multiply this, that becomes positive. So our y of p will be equal to cos t, integral of 1 over u du, then plus sin t. When we integrate, 1 is t, then plus our constant. So we can solve this further. That's y of p will be equal to cos t. When we integrate 1 over u, remember it to be u, then plus this will be t sin t, then plus our constant. Remember our u is cos t. We said u should be equal to cos t, so we replace it back. We have y of p is equal to cos t ln cos t plus t sin t, then plus our constant. That becomes our solution to the homogeneous, so to the non-homogeneous side using the variation of parameters. And remember, we say our general solution is equal to y of c plus y of p. And we find our y of c to be a cos t plus b sin t. So we say our y of t is equal to a cos t, or you can say c1, anything, cos a cos t plus b sin t plus our y of p, which is what? Cos t ln cos t plus t sin t, then plus our c. Then this becomes the general solution to our differential equations. I hope you get this. Please play over the video and you'll be more abreast with it. Do well to check out my videos on how to find solution to non-homogeneous higher order ordinary differential equation using the variation of parameters as well as using the D operator method. Remember to subscribe to my YouTube channel before you sign. Until we meet again, my name is Kepsi.